Hi, welcome to this lesson on calculus, the second derivative. Let's have a look at question 4. So we're given f prime x, so the first derivative of f, and we want to classify any stationary points, intervals where the original function f increases or decreases, and then find the intervals of concavity and if there's an inflection point or not. Okay, so because I know the first derivative already, I'm going to go ahead and find the stationary point. The stationary point is when f prime x is equal to 0. So that implies negative 3 times x minus 1 times x plus 2 is equal to 0. So because it's already nicely in a factorized form, I can use the 0 property of algebra and set each factor equal to 0. So I get x equals 1 for this factor, then it's 0, or x equals negative 2 for this factor. Okay, because we weren't given the original function f, we can't find the y value, so at this point the stationary points have x coordinates at 1 and negative 2. But if you notice, if you expand this out, we'll get a quadratic function. So if the derivative is a quadratic, then most likely the original function is a cubic, right? So 1 degree up. All right, so those are the stationary points. Let's go ahead and have a look at where the function increases. So again, mathematically, the first derivative is greater than 0 for the increasing intervals. So that means we have negative 3 times x minus 1 times x plus 2 greater than 0. So let's put our number line together. So the critical values are at negative 2 and positive 1. Okay, do not forget about this negative 3 outside here. A lot of people will forget that number. That number is still being multiplied by these other two factors. So when we test the regions, we mustn't forget to multiply by negative 3. Okay, because if you suddenly divide by negative 3 out here, then you need to remember to change this inequality sign as well. Okay, so you just got to be careful of the little nuances when you're solving inequalities. Okay, so if I take something bigger than 1, let's say 2, then I'll have 2 minus 1, that's a positive number. 2 plus 2, that's a positive number. So a positive times a negative. So I get negative here. Then a second number between negative 2 and 1. So these are your open dot critical values. So I'll take 0. So I'll get negative for here, positive for here, and negative for here. So altogether, when I multiply, I get a positive. And then if I take, let's say, negative 3, I'm going to have a negative over here, a negative over here, and a negative. So 3 negatives will end up being a negative again. Okay, so where does the function increase? That's when it's a positive. So that's on the interval negative 2 to positive 1. Okay, what about decreasing? Well, that's when the intervals are negative. So that means x is an element from negative infinity all the way up to negative 2. Union joins up again at 1 to positive infinity. Okay, and that's the intervals of decreasing. Now we can do our second derivative test, and we can check for intervals of concavity. So let's do concave down first. So that's the second derivative less than 0. So again, the first derivative was this given function. So let's go ahead and expand that first derivative function out. That's going to be negative 3 times. So if I expand the brackets, x squared plus 2x minus 1x minus 2. So that's going to give you negative 3x squared when you expand out. 2x minus x is just 1x. So that's negative 3x and then positive 6. So the second derivative is taking the derivative of the first derivative. So that becomes negative 6x minus 3. And that must be set less than 0. So solving this linear inequality now, I'll take 6x across. So I have negative 3 is less than 6x, which is the same thing as saying 6x is greater than negative 3. Then if I divide both sides by positive 6, I have x is less than negative 3 over 6 is negative a half. So in interval notation, that is x is an element from negative a half all the way to positive infinity. Okay, what about concave down? So for concave down, or concave up rather, sorry, because we've done concave down. So concave up, that mathematically is a second derivative greater than 0. So again, we're solving the linear inequality. Negative 6x minus 3 greater than 0. If I take the negative 6x over, I get negative 3 is greater than positive 6x, which read the other way is 6x less than negative 3. Then I divide both sides by 6, and I get x is less than negative a half. Okay, so for interval notation, that is x is an element from negative infinity to negative a half. So that is where your graph is concave up. So it's got that shape here. It's above the tangent lines. And then similarly for concave down, it's got this shape here, where it's below its tangent lines. Okay, and then lastly, if we want an inflection point, we need to check, does the second derivative have a point where it is equal to 0? Well, that implies that negative 6x minus 3 is equal to 0. Take over the negative 6x, I get 6x equals negative 3. Dividing both sides by positive 6, and I get x is a negative half. So I would say that that's a point inflection, because to the left of negative a half, so that's this region here, it's concave up. And then to the right of negative half, which is this region here, it's concave down. So it changes from concave up to concave down at the point negative a half. So we can therefore say that x equals negative a half is an inflection point of this original function f. All right, so that's how we would do this one. I'll see you in the next one.